This is our first short answer paragraph from Unit 7, Ladybugs on a Rotating Disc. So we have two ladybugs standing on a rotating disc that's spinning counterclockwise as shown in the figure, assuming that the friction in the bearings of the axle is negative. And as you can see, ladybug A is further from the center than ladybug B. So AI says, is the angular speed of ladybug A greater than, less than, or the same as angular speed of ladybug B? And the angular speeds are the same, okay? Remember, angular speed is how many radians or degrees, if you want, an object passes through in a certain amount of time. And so you ask yourself, well, who goes around the disk faster? And they will both go around the disk in the same amount of time. So angular speed only depends on angular displacement, and their angular displacements are the same. So they complete one rotation in the same amount of time. So 1 point for that with an explanation. Then part 2 says, is the linear speed, right, and that's V, greater than, less than, or the same as the linear speed of ladybug B? And the linear speed of ladybug A is larger than the linear speed of ladybug B. And the reason for that is that, or you could say this a couple of ways. The linear speed of something depends on the distance from the axis, which is larger for ladybug A. We already established that omega was equal. I would have said ladybug A covers a larger linear distance in one rotation than ladybug B. There are a couple of ways to say that. So 1 point for that as well. And now part B says, ladybug A starts walking in a circular path in the direction of the disk rotation. Does the magnitude of the angular momentum of the disk alone, not the ladybug's disk system, increase, decrease, or stay the same? Well, the ladybug is now, by walking in the same direction that the disk is spinning, the ladybug's angular momentum is actually increasing a little bit because, remember, angular momentum is moment of inertia times the angular speed. And so she's going to increase her speed by walking in the direction that the disk is rotating, then her angular momentum is going to increase a little bit. So since there's no net torques on the ladybug's disk system, its total momentum has to stay the same. So if the ladybug's angular momentum increases a little bit, the angular momentum of the disk has to decrease a little bit. So you get 2 points for part B, 1 point for saying that the angular momentum of the ladybug's disk system doesn't change. And then 1 point for saying, well, since the angular momentum of the ladybug increased, the angular momentum of the of the disk had to decrease. All right, part C is a separate scenario, a single ladybug standing near the edge of the disk, a distance 0.9 r from the center. Oh, and that's shown in the figure, which is not shown on my PDF and probably not on yours either, but we don't need it. The rotational inertia of the ladybug disk system is I1, and the disk completes one rotation in 2.5 seconds. So the period is 2.5 seconds. More on that later. The ladybug then walks towards the center of the disk, a distance 0.1 r from the center, and comes to a stop relative to the disk. Now the rotational inertia of the system is I2. All right, so the ladybug has walked closer to the axis, so the rotational inertia of the system has actually decreased a little bit because its mass is closer to the center. Now the disk completes one rotation every 2 seconds, which should make sense to you. When the rotational inertia of something decreases, it should speed up, which is what's happened. So part I here says to derive an equation for I2 in terms of I1. Okay, so we have the angular momentums are equal because, again, there's no external torques. With a ladybug walking towards the center, all of those forces are internal, okay? So that means the I1 times omega 1 equals I2 times omega 2. All right, so we have I2 then equal to I1 times omega 1 and omega 2 over omega 2, But the problem asks us just in terms of I1. So I cannot use this. I've got to come up with an expression for omega 1 over omega 2. Luckily, we know that omega is equal to 2 pi r over the period, right? Sorry, I misspoke. 2 pi over the period, not 2 pi r. The linear speed is 2 pi r over the period. So the angular speed, it goes once around over one period. That's the definition of angular speed. So that's over t1. Omega 2 then is 2 pi over t2. And now I can do omega 1 over omega 2 equals 2 pi over t1 over 2 pi over t2. That goes away. And we get t2 over t1. Right, so a little clever algebra can give us that. Now we have numbers here. T2 is 2 seconds, T1 is 2.5 seconds, and that is 0.8. All right, so what we have here is I2 equals 0.8 I1. Right, and that should make sense because we already said that the rotational inertia of this system is decreasing as the ladybug walks towards the center. So let's talk about the rubric here. 1 point for using conservation of angular momentum using I and omega. 1 point for substituting the speeds, or really the periods, to find out that I2 is 0.8 of I1. So 2 points for, that was actually I of C. So then 1 point for I of C, which says, while the ladybug is walking towards the center of the disk, does it exert a torque on the disk, yes or no? Well, you might think it doesn't exert a torque, but it does. It's an internal torque, right? There's no net external torque, so the angular momentum stays the same, but that is an internal torque. And the way you can tell that there is an internal torque is that there was an acceleration, right? So since omega changed, right, then alpha is not equal to 0, right? If the velocity changes, there must be an acceleration. Well, what causes an acceleration? Torques cause acceleration, okay? So just like back in Unit 2, we decided if there was a force present because the system or object was accelerating, in Unit 7, we can answer the same question. An acceleration is present, since an acceleration is present, a torque must be present. So you get 1 point for saying yes, the ladybug exerts a torque on the disk, and providing evidence that a change in omega means an alpha is present, which suggests a torque. So that's it for the first short answer question.